Okay guys, this video is going to discuss phase diagrams, which are a tool that we use to represent the different phases of matter that are stable under a given set of temperature and pressure conditions. And so here we have a generic phase diagram. You see that the pressure is plotted along the y-axis, temperature is plotted on the x-axis, and you can see that the diagram is broken up into several different regions. This region here at low temperatures and high pressures is the solid region. The region at higher temperatures and low pressures is the gaseous region. And then the region at intermediate temperatures and high pressures, that's the liquid region. And so what these different regions correspond to is which phase of matter is most stable under the given conditions of temperature. And so you can choose a temperature, choose a pressure, and that's going to be the most stable, the stable phase, whichever region you're in. The points where two regions meet, or I should say the lines, the curves, are called coexistence curves. And along this line, so at all of the temperature and pressure values corresponding to this particular curve, we have the solid in equilibrium with the liquid. So this is the liquid-solid equilibrium curve. If you go across the curve this way, you melt the solid. If you go back, you freeze the liquid. Here is the liquid-vapor equilibrium curve. And so at every point along this curve, we have the liquid and the gas in equilibrium. Incidentally, this curve is also described by the Clausius-Clapeyron equation. So we've worked in the previous video a couple of Clausius-Clapeyron equations. That curve, I should say that equation, describes this curve. Here we have the sublimation equilibrium curve. This point here in the middle, where all three regions meet, is called the triple point. Every substance has a unique triple point, the corresponding triple point temperature and triple point pressure, where all three phases of matter are in equilibrium. So at this particular point, the solid, liquid, and vapor phase are all in equilibrium with one another. At high temperatures and high pressures, there's the so-called critical point. At this point, the liquid-vapor equilibrium curve ends. That is, there's no curve beyond that. Beyond this temperature, okay, so the temperature corresponding to the critical point, beyond that temperature, we say that the substance is a supercritical fluid. And beyond that temperature, there's no distinction between liquid and solid. In fact, as we'll see in one of the pictures, the meniscus between the solid and liquid phase completely disappears beyond the critical point. This problem is just meant to illustrate how to use a phase diagram. So what you're supposed to do is to take these conditions of temperature and pressure and then read the diagram to see what is the most stable phase. So taking minus 10 degrees Celsius, which would be somewhere over here, and at a moderately high pressure of 50 kilopascals. Well, it's not very high at all, actually. It's fairly low, frankly. Anyway, it would be somewhere here. So at this low temperature and medium pressure, we would have ice is the most stable phase of water. For part B here, 25 degrees Celsius, which would be somewhere here, and a pressure of 90 kilopascals. I'm guessing that would be somewhere in the liquid phase of water would be most stable. At a higher temperature and a pressure of 40, it's difficult to tell. I don't know whether that curve would be, I don't know whether 40 kilopascals would be above or below that curve for that particular temperature. So it's not very obvious how to answer that question. Really, it's the fault of the question. The pressure should be modified to make it a little bit more obvious. Anyway, you get the idea. You can do the same thing with these other temperatures and pressures to look at the graph and see what's the most stable phase. let's see, here's just another example using a different phase diagram. So this is the phase diagram for carbon dioxide. You can see it's a little bit different. Here, notice that they've plotted the pressure using a logarithmic scale. So it's not a linear scale, it's a logarithmic scale. So that's why it looks a little bit different here. Let's see. So here's the pictures that I was telling you about that illustrate the supercritical fluid. So notice, so what you can imagine doing is you're looking in a window, okay, and what you have here, these are two little floats, okay, so these are floating on a surface. And so you see the line here across, that's the interface between the liquid and the vapor phase. So you're not doing a top-down, you're doing a sideways look through a window. And what happens if you heat the liquid up beyond the critical point is that interface between the liquid and the vapor pressure and the vapor phase disappears, and then these floats will just start moving around, almost like they're just weightless. And then if you cool it back down again, the meniscus will reform, and then you'll have the floats floating on top. Supercritical fluids are often used as green solvents. For example, one way to decaffeinate coffee is to use supercritical, I believe, carbon dioxide to filter the caffeine out of the coffee beans. So just some conceptual questions related to the critical point. The critical temperatures of ammonia and nitrogen are 132 degrees Celsius and minus 147 degrees Celsius. Explain why ammonia can be liquefied at room temperature by merely compressing the gas to high enough pressures, whereas the compression of nitrogen requires lower temperatures. Well, let me go to the generic phase diagram. If you're at a temperature beyond a substance's critical temperature, then no matter what pressure you put the liquid under, so like let's say you're over here at low pressure, very high temperature, beyond the critical point, you can squeeze that substance all you want, but there is no liquid phase because there's no distinction between the liquid phase and the gaseous phase if you're above the critical point. If you cool down below the critical point, so you're somewhere in this region of the graph, and then you start squeezing that gas, start compressing it, eventually you will cross the coexistence curve and you'll compress that gas into its liquid state. So you can liquefy gases below the critical temperature, but you can't liquefy them above the critical temperature. In this conceptual question, if we shake a carbon dioxide fire extinguisher on a cool day, we can hear the liquid CO2 sloshing around. It's under pressure. However, the same cylinder appears to contain no liquid on a hot summer day. Explain these observations. Well, on the hot day, you're above the critical temperature. On the cool day, you're below it. Okay, and so when you're above the critical temperature, you won't detect the liquid phase, but below the critical temperature, you will detect the liquid. And I think part B is the same idea here. So I'm going to go ahead and stop this video here, and we'll pick up with the solid states in the solid state of matter in the next one.